We're now in chapter 2, or almost in chapter 2. We're going to look at some problems that really could have come out of Math 341, which is your linear algebra course. We're doing that because we want to get very familiar with the elementary row operations that really drive any row reduction. And we're going to use that to build our numerical solutions that we'll do next. So first, we'll start with the problem as it's defined from the lecture video, slightly revised, so make sure you use this version, not the one in the lecture videos, and we will put these things together. So here's our nice 3 by 3 matrix. We would like to form AX equals B and ask ourselves, what is B? So problem 1 says start off with building an augmented matrix and use Gaussian reduction to first get echelon form. That's worth 10 points. Now recall echelon form is having 1s down the diagonal, 0s in the lower triangular portion, and the upper portion is what it is. Okay? The augmented matrix means that you're moving B and augmenting it to the right of A. So you end up with a 3 by 4 matrix that we will use in the Gaussian reduction. Question will be, what is the rank of A? And make sure you've got a good reason for why you can answer that the way you can, using standard linear algebra techniques. That's worth 5 points. C, how many solutions exist for the system? And we want you to give a reason for that too. And finally, after you've done that, go on and continue to get reduced form, the reduced echelon form, which simply gets rid of the upper triangular portion and replaces them with zeros, which allows you to pick off the new values in B, and that becomes your solution. Now you may notice in the past I've numbered problems A, B, and C to try to distinguish them from numbers in the book, and now I'm going back to a normal 1A, 1B, and so forth, because we've already got a matrix A and a vector B, so they get kind of confusing if I don't stick with numeric points here. So we'll be doing problem 1, and we'll also have a problem 2, which is extra credit. Keep in mind on this extra credit that you are proving something in general. A is an arbitrary matrix, which means it is not this one up here. It's anything. It isn't necessarily square. It could have more rows than columns. It could have more columns than rows. But whatever you have, prove that if you form a matrix B by taking A transpose A, then B will always be symmetric. So that's worth 5 points. And then also, if A is not square, will B be square anyway? Or will B be rectangular and justify your answers? So that is the revised homework. It's not revised much, but that's your homework. And now let's go ahead and take a look at some hints on how we could put that together. So here's our augmented matrix. We just took column B and augmented it to matrix A. Then we will start doing ordinary row reduction. Now I'm not going to give you all the row reductions here, obviously, because that's your job to do in the homework. But you can do this in just about any order you want. You could take row 3 and subtract row 2, and that would very nicely put a 1 where you would like it in the upper left-hand corner. Or you could take row 3 and subtract row 1, and you would get a nice 0 down here, which is something you also want. You can do things in any order you want, and if you don't make a mistake, you will only be able to come up with one particular reduced echelon form. So use your elementary row operations, reduce the argument to echelon form, then look at the trace. Remember, when you get echelon form, you will get 1s down this major diagonal. You might get some zeros even, but you'll get 1s or zeros, and when you add them up, that will be the trace. How is the trace related to the rank? Also, what does full rank mean? Well, it means that the rank is equal to the row dimension. So what does that imply about the number of solutions? You may need to go back and check the book on that, on how that works out. And then finally, you just continue on until you get zeros up here in the upper right-hand portion and 1s down the diagonal. You keep the zeros in the lower triangular portion, and that's in reduced form. How do you pick off the solution from that when you get to that point? Okay, so that's what you have to do. That's your hints for problem 1. It's a standard Math 341 problem, and go ahead and check your work when you're done, because if you plug the answer back into the problem and it doesn't solve it, then you know you've made a mistake somewhere. Okay, we'll come back and work that problem later, but let's also look at hints for problem 2. A problem 2, okay, it is a extra credit problem, but it's pretty straightforward to do. It's worth doing. The question is, prove that A transpose A is symmetric. If you do it, keep in mind that this matrix A is now arbitrary. It is not the same matrix that we did in problem 1. It's not even necessarily a square matrix. It might have more rows than columns. It might have more columns than rows. Now, you should go back, if you want to do this the easiest way, go back to your linear algebra tools and ask what happens if you have a product of a matrix, just like C times D. What happens if you take the transpose of the product? How is that related to the individual transposes of the matrices being multiplied? Look that up, and you can solve this problem really easy that way. You do need to ask whether the matrix multiplication is possible, because not all matrix multiplication is. Can you always take A transpose A? You should need to address that issue. So with that, give it a shot. There's 2 ways to do it. There's an easy way, going back to looking at linear algebra rules, and there's a difficult way, looking at all the indices of matrix A1 and A2, which in this case are A transpose and A. You still need to address what the dimension is of the product and why that multiplication is legal.